So we will now look at runtime support needed for hardware transactional memory. There is some software involved in hardware transactional memory, but the huge difference between software transactional memory and hardware transactional memory is that the memory accesses are done completely in hardware, and no extra instructions are used for logging the memory accesses, meaning the addresses that were used. Okay, the first requirement on a transaction is that it's a region with a single entry and a single exit. So no go-to from anywhere outside the transaction to the middle of the transaction is forbidden. Is permitted. They are completely forbidden, and that's a good thing. And no go-to from inside the transaction to an arbitrary place outside the transaction is allowed either. And almost all source code consists of regions of single entry, single exit parts. Okay. In addition, there are no exceptions permitted, and by exception here is meant exception in the CPU pipeline, such as divide by 0, which results in an exception unless it's a floating point, in which case it gives infinity as the result, and segmentation fault and other things. Such exceptions are not permitted. This has nothing to do with Java exceptions, which is a software feature. Okay, so the operating system needs to copy some register values in order to restore them after the transaction, in case it fails. And also for deciding which transaction should fail. First, 3 registers, and this is nothing that you need to worry about for the exam, but there is a register used for a thing called the global offset table, and that is used for linking code during execution. There is a desire to have only one copy of, for instance, malloc or printf in a machine, so that different programs which use these functions can use the same instructions. And for that, something called position independent code and shared libraries can be used to handle this. So the operating system can see that certain library codes are already in use, so there is no point in loading them from disk another time. I will not ask about that, but in case you are aware of this, it may be interesting to know that this must be said. Okay, and then if there is a failure, there must be some code that executes the register restore. So this is machine code that the compiler selects, and it will the transaction will jump there when it fails in order to restore the registers. Okay, but now we come to something interesting, which I may very well ask about at the exam. Namely, there is on power machines something called a time-based register. A time-based register is a register which is incremented with a certain frequency, and it can be used for very accurate timing. The worst thing to do timing, well, sometimes it can be useful. It is to ask the operating system what time it is twice, and then take the difference between that. But as we know, making a system call is expensive, so that should be avoided. This register can be read from the application program, and we can calculate how many clock cycles that have passed since the reading of this register. Okay, so why is the operating system interested in this? It can be used to determine the age of a transaction, and we will see soon why that is useful. Okay, there are also other registers which may need to be restored, saved and restored, and they are determined by the compiler, and they take the current register usage into account. Okay, so if there is a conflict, the kernel is invoked, and it has to decide which of two transactions should be aborted. And the reasonable approach is to assume that the older transaction has done more work than a younger transaction. So it's better to abort the younger transaction. And therefore, the copy of the time-based register at the transaction start is used to decide determine which transaction to keep. And then the cancel transaction is retried. But it's not retried an unlimited number of times. After a certain number of times, that transaction is switched to become an irrevocable transaction. And that means it cannot fail. I mentioned previously here that the transaction can be non-speculative. Normally they are speculative, but after they have failed too many times, they become non-speculative or irrevocable. And they cannot crash unless they contain a bug, of course. So how can we assure that there is some transaction that cannot fail? Well, it's done using a lock called the irrevocable token, and there is only one of this, and the one which the transaction which is able to take this lock cannot fail. Okay, and then when this irrevocable transaction has completed, it can be a good idea to mark this so that it will not try and fail so many times in the future. Instead, it can be marked as problematic, and what this saved then is the start address of the transaction, so that some address of the transaction, so that it can be identified uniquely. And then for future failures, a problematic transaction can switch to irrevocable at the first time, instead of doing many tries.